According to the previous example, this is the root locus or the final root locus sketch that we got. So in this figure, actually, we can see all the rules that we learned about drawing the root locus or sketching the root locus. So for example, you can see the number of, as we said, we see the number of branches, which is 3, depends on the number of poles. We can see the where is the root locus on the real axis. Okay, it's on the left of the odd number of zeros, for example. Then I mean, or balls. Then we see the asymptote. We have 3 asymptotes because the difference between number of pole and number of zero is 3. So we have 3 asymptotes. We have also the intersection with the imaginary axis, and this is according to the rule number 7. And also we have the angle of departure, since we have complex poles. So we have 2 complex poles, so we have 2 angle of departure. We do not have any angle of arrival because we do not have any complex zeros. As we can see here, that the left side, we said if the poles, if the poles are located on the left side or left half of the x-plane, so the system will be stable. If the poles are located on the right, so the system is unstable. So based on this graph, we can identify the stability as a performance metric or performance parameter of the electrical control system. As we mentioned previously, that in chapter 4 we said there are 3 main criteria. One is related to the transient response, one is related to the stability, and the third is the steady state response. So actually from root locus we can know more than stability. Okay, so stability is one part and is one of the concern of the root locus, but also we can know from the root locus other parameters related to transient response, as we can see in this video. So the stability in the root locus here, and we say this is the stable region, this is the unstable region here. So if the poles when we say the root locus represent the path for poles, that means the poles will be changed in on this path. We cannot have pole here. The pole cannot be placed in any area, rather only on this path. All the poles or the expected poles by changing the value of k or of the gain must be located on this path. For that, this is why we need to find the root locus. All the poles must be on this root locus, either this one or that one here. So as we can see here, according to the root locus number 3, all the poles will be on the left half plane. So the system will be more stable. For the according to the root locus number 2 and number 3, here we can see there is a border or there is a margin here. At this point, the k we said equal to 150, and if k is increased more than 150, so the system will start to become unstable because it goes to the unstable region. If the k is less than or equal to 150, as we mentioned before, the system will be marginally stable. If the system is less than 150, so our system will be stable. Always the value of k change from 0 to infinity. Okay, the minimum value is 0, the maximum value, and then goes to infinity. The value of k at open loop poles of the transfer function is equal to 0. That means you can see here at k at this pole, the value of k start to be 0, then increase. If I ask you, maybe if we calculate k here is different, it's more than 0, it's more than 0, all this area. The same here. At this point, the k is equal to 0, then the k start to increase. Please refer to the example or the first example of the table in the beginning of this chapter, and you see the impact of changing the value of k on the location of the or on the values of poles for a closed loop transfer function. So we said k equal to 0 in the open loop transfer function. Then for the closed loop, k starts to change, increasing. I mean, when k change, the location of pull will be increase, or change. Okay, move. So this is how we can use the root locus for to analyze the system stability. We have two regions, stable region and unstable region. On the left, stable. On the right is unstable. So by locating the root locus on the left side, so this represents the area of stability of the system. On the right side, this represents the area of instability for the system. Okay. Also, for each point at the root locus, that means each point on the root locus here, any point here, we select. Okay, it has, or we can get several parameters. We can find the value of k. So we say the value of k, for example, in the beginning here, in the first case, the value of k is equal to 0. Then here we have another value of k. At each point on the root locus, we can find the value of k by applying the condition for magnitude, which is kjs hs equal to -1 or k equal to 1 over kjs hs. So for each value of on the s here, or on the sigma axis, we can calculate the value of k. This is one of the parameters that in addition to the stability, we can calculate the value of the gain for each value point on the root locus. Then we can find the percentage of overshoot. Overshoot is one of the parameter or performance for the second order system. As we talk in chapter 4, we said overshoot was one of the parameter for the transit system of second order system, or also TS, or settling time, is one of the parameter either for first order or second order system related to transit response. This all related to transit response actually. All these parameters we can find from the drawing of root locus. If you try to apply the formula, the method to find the root locus by using MATLAB, and you generate the root locus using MATLAB, on the graph of the root locus, if you place your pointer on the graph, so you are going to see different parameters. You are going to see many parameters related to the value of k, overshoot, settling time, natural frequency, and also damping ratio. So from the graph we can find all these values. So settling time, natural frequency, and damping ratio, this all more related to the second order system transit response. So these are the formula that we need to follow, or we need to use, in order to calculate the value of the damping ratio, the value of settling time, the value of the gain according to the root locus graph, or from the root locus graph. As you can see here, so if you have the root locus, the one that we generated before, then we draw line from the pole 0 here, or from the point of origin to the root locus. The length of this line represents the natural frequency. So this is how we can find this parameter from the root locus graph. You have the root locus, then you draw line from the 0 here, from the point of origin, or from the pole at the origin here, to the root locus, to the other pole here, the second pole, which is a complex pole. Okay, the length of this line, or the length of this vector, represents the value of natural frequency. The angle between this line and the sigma axis represent theta, and from this theta angle here we can calculate the value of damping ratio by saying damping ratio will equal to cosine theta. So if I find theta equal to 30, cosine theta will be the value of the damping ratio. If we say theta is equal to 0, then cosine theta will be the value of the damping ratio. Also, if we draw line from the poles on the root locus here to the value, to the sigma axis or real axis, we are going to find the value of negative sigma d, which is a number here in the negative side, and this number actually will equal to zeta omega n. So if we have already zeta, we can find the value of, if we have the value of theta here, and cosine theta already know, so we can calculate the damping ratio. After we calculate the damping ratio, we can find the value of omega n. Okay, because we said damping ratio here is equal to cosine theta. So we have the theta, that means we have damping ratio. If we have damping ratio, we have the value of omega d from the graph here. We can find the value of omega n, or the frequency or natural frequency. Also here, the crossing, I mean the on the if we draw a line from the complex pole to the real the imaginary axis, this should give you the value according to the transit response characteristic that we studied in chapter 4. This will give you the value j omega n 1 minus zeta square, and also this equal to j omega d. Actually, from this one, if we know the value of j omega d and we know the value of zeta, we can find the value of omega n. That means you have more than one method to calculate the value of natural frequency in this graph. The value of the pool here, which is S1 and S2, and the complex pool, should be, we can find it, or we can apply for it the formula for zeta omega n plus minus omega n, zeta square minus 1, and this we said zeta we have over dam, under dam, and critically dam, and so on. So this is all the values we can extract or we can find from the root locus that given. But in order to find the correct values, we need to draw the root locus exactly according to the value that we calculate. Okay, so you need to highlight the position of poles, you need to highlight the position of zeros, you need to highlight the angle of departure, angle of arrival, I mean breakaway and breaking point, and so on. After you have the final graph, from the final graph you can find the value of zeta, the value of omega n, the value of theta, sigma d, or real frequency here, I mean real value of s, j omega d, or natural frequency. Okay, so this is how to use the root locus in order to calculate the different transit response for the control system. Here we have one example in order to calculate the, some parameters for the root locus, like k, the value of k, the breaking point, and also the angle of departure. So we have, this is the transfer function, consists from 1 0 0 1, which equal to -2, p1 and b2. We have two poles here. We need to solve this one or this polynomial, or this second order ordinary equation in order to find the value of s. So we should have two s here. One is p1, one is p2. So the question is said root the or sketch the root locus. We said we can draw a general form of the root locus by applying the first 5 rules. But in order to refining or finalize the sketch, we need to apply the rest of the rule. He said sketch the root locus, find the imaginary axis crossing. This is rule number 7. Find the gain k. So this is really the value of the gain at the j omega axis crossing. Also, he wants the for related to the crossing, which is rule number 7. Find the break-in point, which is rule number 6. Find the angle of departure from the complex pole. So this is rule number 8. Okay. So give the example here. We can, I mean, by finding the value of zeros, value of pole, and applying the rules from 1 to 5, we can draw the sketch or sketch the root locus. Then we go to find the other values. So as we can see here, this is actually the graph. So we have the value of the, which is s square here, the place of the pools. We have two complex pools, actually 1 and 2, and we can find these pools actually by applying either using the calculator to find the roots for this equation, or by using the formula -b plus minus p square minus 4ac over 2. So by applying this one, so we are going to have negative b, which is -4, so it will become +4, plus minus b square, which is 16, minus 4 times a, which is 1, times 13 over 2a. So 2a will be 2 times 1, because a here equal to 1. Okay, then this will be like 4 plus minus 16 minus 4 times 13, so it will be 26 plus 26, 52. So 16 minus 52, 16 minus 52, it will be 36 negative. So this will be like -36. Okay, over 2. So now we have 4 plus minus, when you have this, the square root of negative 36, it will be plus minus j6 over 2. So this will be like 2 plus minus j3. So S1 here, or the pole number 1, will be 2 plus j3. B number 2 will be 2 minus j3. So if we go here, we can find this is 2, this is minus j3, 2 minus j3. This is the first pole. This is 2 plus j3 is the second pole. And the 0 that we have from based on this equation is at negative 2. So this is the 0 point. This is the 0, this is the pole. So we have two zeros and we have, I mean, two poles and we have 1 0. That means the difference between number of poles minus number of zeros equal to 2 minus 1 is equal 1. So we have 1 0 at infinity. Okay, and since we have 1 0 at infinity, also we have one, the number of asymptote here is equal to 1 asymptote only, one asymptote. And then since we have only one asymptote, that means we have one angle for asymptote. Since we have one angle of asymptote, the angle of asymptote will be 2k plus 1 by over mb minus nz. So this equal to k equal to 0 since we have only one asymptote. So we have pi over mb, which is 2 minus 1, so it will be pi. So the angle of asymptote will be 180. So if we draw the asymptote on the for this line, it will be like this one. It's just one drawing on the real axis of the circuit, I mean of the system, of the S-plane. Okay, so in order to find the crossing, which is the first, after we draw this one, actually, why do we draw it in this way? Because we said that the root locus must be symmetry around the imaginary, around the real axis. So since we have one pole here, one pole here, usually the root locus start at the pole and at the 0. So this root locus will start at this pole, will go this way until here. This there is here one point, we call it break-in point, because this is the break-in point is in the real axis, allow the root locus to go to the 0 here. And the second root locus will start at this pole, for example, and go there to the break-in point, and then it's go to infinity. Why go to infinity? It will go to infinity with the asymptote here. The asymptote has an angle of 180, so it will go to the infinity through with the asymptote in order to reach the 0 at infinity. Okay, so this is how the general form of the uh, root locus here. In order to specify the point of crossing and know the break-in point, so we need to apply the form, I mean the rules, the rest of the rules. Also we need to find the angle of departure. For example, here we do not have angle of arrival because our 0 is on the real axis. So in this case, just we are going to find the I mean apply the rules, which is rule number 6, rule number 7, and rule number. So in order to find the crossing here, we start with the crossing point based on the question here, because he asked after you draw the root locus, find the imaginary axis crossing. So in order to find the imaginary axis crossing, we need to find the characteristic equation for the closed loop transfer function. So we are going to apply the, I mean convert, or this is GS here, in order to find the TS. And then we to apply the rows table here, we need to find TS, and then we find the characteristic equation. So it will be GS over 1 plus GS HS. Actually, because here unity feedback, that means HS equal to 1, so there is no HS. Okay, so it will be GS over 1 plus GS. So you just try to substitute for GS by its value here, and GS here by its value, then simplify. You are going to obtain this value of TS. TS will equal to this one, or to this value. Now we are going to take this characteristic equation, which is S squared plus K minus 4S plus 2K plus 13. This is the characteristic equation that we are going to use in our rough table here. So it is s squared s1 s0. Okay, so when we draw the or construct the rough table here, we are going to make the coefficient or variable here. It's 1, and this 2k plus 13 for s0. This k minus 40 for s, and here it's equal to 0. Actually, k minus 14 or k minus 4, it is the same because we said last time we can divide it by then I mean here k minus 4, sorry, according to this one it's k minus 4. Okay, so after we substitute here, we in order to find the crossing, we need to find which line can be goes to 0 or become entire row of zeros. So the first line cannot, because we already have one, so cannot become all zero. So we come to the second line. Yes, it can be all zeros if the value of k equal to 4. So if the value of k equal to 4, then this line will become all zero, because 4 minus 4 is 0, and then here we have 0. Then we have the second case of or second situation of the row table. So we need to go one step before in order to write the equation. So we write the equation here for the previous line, which will be s squared, because we have 1. So it will be like 1 s squared plus 2k. K already said k equal to 4, so it will be 8 plus 13, so it will be 21. Okay, so it is like s squared plus 21. So this is the equation here that we can write from the first line or first row. This will equal to 0 in order to find, for example, if we want to solve this equation to find the value of crossing, then s squared will equal to negative 21, or s will equal to set negative 21. So this will be j plus minus j 21. Okay, so this is the crossing here, set of 21 plus minus j value. So this crossing point is negative set 21, and here is positive set 21. So these are the crossing point here. The crossing point is at set 21, and the third part here, which is what is the gain of k at the j omega axis. He wants to find the value of k at this point. What is the value of k here? We already say here the value of k is equal to 4, because at this point, in order to find the crossing point, we substitute for the value of k by 4. So when we put the value of k is 4 in this parameter, we got the value of uh, 22 times 4, which is 8, plus 13, which is 21. Okay, so then the value of k equal to 4. The next part is find the break-in point. We said the break-in point, we should have break-in point or breakaway point only if we have bulls or either bulls or zeros on the uh, real axis. So here our bulls are at the imaginary axis, so at the image are complex and are not on the real axis, so we do not have any breakaway point because we do not have two bulls on the real axis, so we can have breakaway point between them like this one. This we call it breakaway point. Okay, but we have 1 0 on the real axis here, and the other 0 at infinity with asymptote of 180, so it will be on the same line. Since we have two zeros on the real axis, why I know this is on the real axis? Because its asymptote has angle of 180, so it is on the same line of real axis, and they have 1 0 here on the real axis. That means I should have break-in point, which is here. This is the break-in point, but I don't know the value. So my task is how to find or to calculate the value of a break-in point at this point. Okay, so in order to calculate the break-in point here, so we are going to search for the minimum gain to the left of negative 2 on the real axis that yield negative 7 at the gain of 18. Why the gain of 18 here? The gain of 18 is the gain where the point or where the value of the k will crossing with the imaginary axis. Actually, you can just find the value here by applying the formula, by applying the differentiation method that we learned before, or by applying the point, I mean either the differentiation method or also the using the formula we said 1 over sigma plus z1 equal summation of 1 over sigma plus z I equal to summation of 1 over sigma plus pi. Okay, so you have two methods in order to find the value of uh, the value of break-in point by applying these two methods actually, because we have only one z. I mean, what you have only one zero, and you have here two bulls. Both bulls are imaginary, so we don't want any value of imaginary here. The imaginary values will not be located on the real axis. Okay, for that there is no break-in point here. There is no breakaway point. There is no breakaway point because our pools are complex. So there is no breakaway point. We only have break-in point. And in order to find this break-in point here, we need since I have the 1 0 here, and I have this circle or this semicircle will cross with the real or the real axis here. I need to find the minimum gain to lift the minimum gain for the real axis that yield -7 here, in order to find the -7 at the gain of 18 value. Okay, so the value here is -7 of the break-in point, and then we need to find the angle of departure, find the break-in point, then find the angle of departure. Since we do have a complex pool, so we have angle of departure, and we do not have angle of arrival because we do not have any complex zeros. So here in order to find the angle of departure and angle of arrival, we need to draw the line. We need to draw the vector from the zeros and bulls to the point that we want to find the angle of departure. For example, if we want to find the angle of departure for this one, actually usually we do not directly draw to the bull. We draw to a point near to the bull. Okay, in order to calculate the vector length, then the vector angle, then we can find the departure angle of this. So in order to find the angle of departure here, we need to apply the formula that said summation of angle of 0 minus summation of angle of the bull equal to 2k plus 1 180, the one that we mentioned when we highlight how to calculate the value of the angle of departure or angle of arrival. So then we draw line from the zeros. So we have 1 0 here. We draw line to the point epsilon, which is too close to the angle here. Too close to the bull. And then we draw another line from the other bull, which we don't want to calculate in the beginning. So here, this is another bull here. This bull has angle of 90° with the horizontal axis. So this is the 90° of that bull. This angle has, or this bull, this zero has the angle of theta, which is the value of the, we can call it like theta 1. Okay, so the value of theta 1 here, or tan, it is tan inverse opposite, which is 4. The opposite, which is 3, because from this point to that point is equal to 3. Okay, 3, and adjacent, which equal to, here we have 2, here we have 2, so it's become 4. So tan inverse 3 over 4. So in order to find the angle here, it is tan inverse 3 over 4. We can find it. So after we find the value of theta 1 and we find the value here, which is 90, we can find the angle of departure, which is theta here. Okay, because we have the formula said the 100, either we can say the angle of departure here equal to summation of angle of 0 minus summation of angle of pulse plus 2k plus 1 times 180. Okay, according to this formula, actually the formula that we have for the angle of departure and angle of arrival. So you can see here 180 plus angle of zeros, 180 plus angle of zeros minus angle of pole. This is if we want to find the angle of departure for a system according actually to this formula here when we study the angle of departure and angle of arrival. So this is the angle of departure, 180 summation of angle of zero minus summation of angle of pole. In this case, in our example, we have only 1 0, which is at 2 -2. Its angle is theta 1, we said, and it's tan inverse 4 over 3 over 4. We can find angle of ball, which only we have one other ball which angle is 90, so we have 180 here, so we can find the value of angle of departure according to this formula. Okay, so the angle of departure is 100 233.1 in negative. That means when the root locus leave this bulls, it will leave it with the angle of -233. -233, that means we are going to calculate. Just if we remove this one, we are going to calculate. This is the bull here. We said the angle always calculated with the horizontal axis. This is the horizontal axis. When we said -233, that means this is -180. This way, this is -180. Then we want 233. That means it will be in this area. So the root locus will reverse with this one. So -233.1 actually is equal to angle of 180. 233.1 minus. It is the angle of 53 plus 90 is the angle of 143. Okay, so if we calculate the angle from this point to that point, it will be 90 plus the rest for to reach to the 180 here. So it's -233.1. So this will be the angle of departure. The same for the other ball. The angle of departure should be symmetry. So instead of -233, it will be +233. So we can see here the figure how this is the angle here. We just remove this. So now if we can see here, this is +233.1 positive, and here is the -233.1. Okay, and the point here, this one is -7 breaking point, and here the crossing is J21 negative J set 21. So this is how we can find the different value which is related to the root locus if we have the general form of the root locus in the beginning.